So, good morning everyone and welcome to this Know-How Solutions webinar. My name is Björn Skjonberg. I work as FIE here at Know-How at headquarters in Malmö. So, this is session 1, Debug your embedded system using Lauterbach. So, this webinar is a webinar in a series of 3. So, today I will talk about what you need to get started to debug your embedded system. I will show you what you can do with basic debug. So what I mean, what you can do when you only have a JTAG connection and no trace possibilities. And we will end this session with a Q&A. Tomorrow, at the same time, I will show you what you can do with trace. So either if you have some embedded trace buffer on your target, or if you have an external trace hardware from Lauterbach. So what type of performance measurement can you get? Code coverage, and also what reports you can get with code coverage. I will show you cache analysis and also what you can do with context tracking system. And then on Thursday, same time, 9 o'clock, I will show you what you can do with Lauterbach and how you can add your Lauterbach to your continuous integration. So it's more or less adding your Lauterbach to your already existing software or system component test. So a little bit about the APIs that are available from Lauterbach and also how you would think if you would like to add them and use this in the test automation. And also what types of reports you can get out of that. But that's on Thursday. Before we go into the technical stuff, let me just give you 3 slides on know-how and who we are. So we work in these 3 fields: embedded design and development, software quality and test, and functional safety and embedded security. And we're actually celebrating 35 years this year, so we have been around for quite a long time. We have headquarters in Malmö in southern Sweden. We also have offices in Copenhagen and in Helsinki. We are about 18 employees in total. So we supply the Nordics and a little bit of the Baltics with our solutions. So the solutions that we supply come from these suppliers. So I hope you at least recognize some of them. Today we will talk about Lauterbach. Okay, so back to the technical part. So my system today. So I'm using a Panda board with Linux. It's an SMP system. So it's a chip from TI called OMAP 4430. So with SMP it means it's symmetrical multiprocessing, and in my case I have 2 Cortex A9. On top of my Panda board, I'm running a Linux kernel, which is 3.1.2, and I am connected to my target via the JTAG connector that's available on my board. So what do I need to get started? Well, first of all, you need the Lauterbach Power Debug module, which is this one. So this is generic, which means that it works for every architecture, no matter if it's ARM or PowerPC or whatever you might use. You need a debug cable. So the debug cable is connecting the Power Debug module and then to the target via a connector. So in my case, I need a debug cable for ARM, and I need to have the license for Cortex A, because this is the kernel I will debug today. I need to use the right version of Lauterbach software, and the Lauterbach software is called Trace32. So since I have a 64-bit Windows machine, I will use the 64-bit Windows version of Trace32 to debug ARM. So it will be called t32marm.exe. So of course, if you have Linux or Mac, 64-bit or 32 bits, there are these executables as well for Trace32. So it doesn't matter which RTOS you have on your host. I will use a VM Linux image, which I have compiled with debug symbols, so -G in GCC, and I have it stored on my host. I have applications that I have also compiled with debug symbols. So to get the source code debugging, so to speak, I need the source code stored somewhere on my host. So when I load the kernel and when I load the applications, I will tell Trace32 where the source code is, and then he can map symbols with source code together. And since I'm using Linux on my target, I will use one of the RTOS awareness files from Lauterbach. So this is available for more or less every RTOS that you might need to debug on your embedded system. So this is what I can do with the debugger. So I can put breakpoints, I can single step forward, I can view the memory, so registers, peripherals, variables. I can do flash programming. I have my RTOS awareness, so I will use Linux because I'm running Linux on my target. I can trap segmentation faults, and I can do something called benchmark counters, which is specific for Cortex-A. I will talk about more of that later on in the presentation. And then you can also use Trace32 in what's called run mode debugging. So it's very similar to the GDB, but I will not show this today. So this is the contact information. So for technical questions, please contact me. And for sales questions, please contact one of my coworkers in the respective countries. Okay, so I have Lauterbach up and running. So you see down here that I'm running. I have a Linux 3.1.2 running. So I already preloaded the Linux image to my target, and I've loaded the symbol to the debugger. So if I were to break the execution, it will no longer be possible for me to give any input to my Hypod terminal because the system has come to a complete stop. Okay, so let me just put up some windows, and then I will start talking a little bit of what we see. We will put a spotlight on that one. Okay, so this is Trace32, the software that we're using to communicate with our debugger. And this Trace32 window or Trace32 software always look the same. So it doesn't matter if you have ARM or PowerPC, the experience will always be the same and the functionality will more or less be the same. So when we have a look at the menus, we have the standard menus, which we have here. So they always are available to you. I have OMAP 4430, which is giving me all the peripherals that I have here. So if we have a look at the, perhaps not this one, but if we have a look at, let's say, the display controller, so I can just say, okay, channel 0, and then we say this register here. So if I highlight the register, I will get an information of what this is doing. If I double click, it will be set here in the command line of Lauterbach, and I'm able to alter the value of this peripheral, and sorry, this register. So, but I don't want to, so let's keep it in the way it was. So if you have your own developed peripheral at your company, you can of course write the same type of menu that will give you the same access which I'm showing right now. We have a Linux menu. So this is because I've told my debugger that I'm debugging Linux. So this will give me quite a lot of possibilities. So I will be using this quite a lot today for process debugging and library debugging and so on. So let's go ahead and load an application, and then I will explain a little bit more the different steps. So we're going to do process debugging, debug process on main. My process is called bit. So this will load the symbols of the process and put a breakpoint in the beginning of main in the process bit. So I tell Lauterbach that it's bit I want to debug. I open my terminal and then I say bit. So there we go. So we stopped at the beginning of main. So we have the bit. So this is the process I have right now in my system. It has a space ID, which is 220. So the space ID here will correspond to the space ID that we have in our data list window. So the user will always know at what process am I looking by looking at the space ID. So the space ID is something that Lauterbach has done to make it easier for the user to know this. I have stopped, so bit, core number 0, stopped at breakpoint, and this is a stack frame of bits. So if I were to click down here and say core number 1, the stack frame will shift because core number 1 has stopped in the swapper, which is the kernel. Core number 1 is here, so the kernel always has space ID 0, and we see that it's the same address out here, so 0 in the beginning. We also see that the registers will be different because I put this spotlight on, so they will be highlighted when the value is changed. And this is of course quite natural because now I'm looking at core number 1 and previously I was looking at core number 0. So of course the registers will be different. I can also go in and have a look at the different stack frames with locals as I wish. If you find something interesting that you need to look at, just click it and we will be able to see the registers. Okay, so you can of course step either in assembly mode or if we switch mode to high level mode. So we see here we can step the high level, so to speak. We can also have the step over. So if I don't wish to go into this sleep function, I can say step over and it will be a breakpoint here, and then I will stop at the next instruction. Okay, so I will go ahead and change SW. So we can either look at SW in a watch window, or we can say look at SW in a dump. So no matter how I do it, I can of course change the value of SW because I have the JTAG. So I can do a little bit what I want with the memory, so to speak. So either I go ahead and double click in here, or I double click in memory, or I double click in the data list window and I set SW equal to 2. So now you see we have 2 here and 2 there. So if I put breakpoint at MemFrak, let's go there, and let me just remove some windows, so make it a little bit more easier to see. So we will be looking at MemFrak now. So MemFrak is a pointer. So we can right click on MemFrak and we say either display dump, so display the value that MemFrak is holding, but because it's a pointer, it will be more useful to display the value of the pointer where the pointer is pointing to. So indirect dump, which we have here. So as you all can see, we're now in the space ID 220. So this is the virtual addresses because Linux is using the MMU. So he is translating physical addresses via the MMU to virtual addresses. So this is not the actual address of where this code is residing on my target. So to get this, we can always ask the debugger to give us the actual address. So I'm saying, give me the physical address of space ID 220 and address 14,000. And then I will add a spotlight to this, so we can see how the values are changing. Also, because MemFrak is holding the pointer to a frame buffer, there's the image stored in MemFrak. So I can, of course, have a look at this image. So like this, and I know the image is 250 by 250 pixels JPEG. So when I start stepping, so you see here that the memory in the virtual addresses is being changed as well in the physical addresses. As well, you see the image is being updated. So when I step the code, the image will be updated and the memory will be updated correspondingly. So this is just some different ways of how you can look at memory. Okay, so now we're done debugging bit, so I will run for a little bit. I will remove the windows and I will see at my processes. So I have to remove my symbols, which I will show you in the next step. So I will delete process symbols like that. And then I can either go ahead and kill the task via the hyper terminal, or I can kill it from within Trace32 software. So I will do it like this. Then we will run. So now we are running. We see it down here. And we see that bit has been killed. Okay, so let's go ahead and make things a little bit more realistic. So I will now add multiple processes to the target. So I will go ahead and say handling and start multiple processes. So this is a script which I have pre-made here at Know-How. So it's telling me to start bit again. So we start bit. And then we will see that we will start a few other processes like this. Okay, so first of all, what I didn't tell you before. So we have our symbol. So symbol list tree will give us all the symbols that are available that we have loaded to our debugger. So if I go ahead and click in bit and we say bits main and we say I want to go to main function of bits main, I can double click this and the source code for bits main will appear. And this is possible for all the symbols that you have loaded. So doesn't matter really which one you pick. Also, you can see that each process has now its own space ID. So I will be able to tell in which process am I looking. I have also gone ahead and put some breakpoints in the various functions. So if I run, you will see that the breakpoint will be highlighted here. You see which process we have here and what core, and we see stopped at breakpoint. So this is quite nice and handy. I've also made it a little bit easier for the user of Trace32 to know which process am I in. So I've added a color here to the left, telling that okay, when we are in proffer, it should be yellow. So I've just created in something called group. So I just give them different colors, and then I'm able to save this in a script. So let's say group, like this. So if you have something that you're okay, this is good, this I want to save. So we can reset the groups, and then if we say do and then group, the groups will come back. So everything that you do when you feel like, okay, this I want to save for later, you can always use the store button that you have in many of these Windowses. Okay, so this is quite nice. You can see which one. Also, if you're asking Lauterbach to, okay, I want to have a look at the main function. So because usually there are many mains, so there are usually one main in each process, Lauterbach will ask you when you're tabbing, do you want to have a look at the main in linkage main, in bits main, or in proper main? So it doesn't matter that the function has the same names internally. Lauterbach uses something called what's the long symbol name. So it's always able to know which one you're meaning. So when we are done with doing the debugging, we have again, of course, to kill our processes. So I've done a script that's doing this for me as well. So it's removing all the symbols and killing all the processes. And it looks like we are done. Before we go into next topic, let me just give you a little bit on customization of the GUI. So as I told you in the beginning, these are the standard menus. And this menu, Demo Panda, is something that I've created here at Know How. So I've made this because when I do demos, I need to remember what I'm supposed to demo. So I put the most common things that I like to show, and I put them here in the menu, and then I have a script that is, so when I click this, the script will be executed. So this you can do as well at your company. So if you have use cases that are quite commonly used, you can always go in and put them in the menu. And then if you have perhaps users that are not so experienced with the Trace32 GUI, can just go ahead and click this menu, and it will set up the whole debug session for them, or it will take some ROM dump or do some error detecting or something like this. So it's quite nice to have this and be able to customize your GUI. I've also put in a button, so this is for the stuff that I use really often, which is start and restart of my system. So this is of course also available for you. So it's quite easy to add your own buttons to the GUI. So next, what I want to show is the how to debug a library. So to debug a library, I need a process which is actually using the library. So I will go ahead and do the process debugging, debug process on main. So the process is called add, and I will say OK. And then I will say add, and I would like to add the numbers 1 and 3 together. There we go. So we stopped in the beginning of main. Now we see that the symbols are loaded. If we have a look in add, we see that it is using what's called libadd. And if I double-click libadd, I will come to the dynamic linker of Linux. So since I don't have the source code for this, and because I have not called my library yet, the library is not in my virtual space. So first of all, I need to go ahead and add symbols for the library. So I do that by Linux, library debugging, load symbols. So the process name, which is using the library, is called add. And the library name is in binaries, Cortex A, libadd. So this is a .so, which is a shared object. If you're using Windows CE, for example, it will be called a .dll. So the process is the same as I'm showing right now. So we will open this and we say OK. So we have now added the symbols for libadd. So when I click libadd, it will get me to the library. So I will put the breakpoint in the beginning, because still if I try to access libadd, it will not find it because it's not yet linked. So when I hit go, I will stop at libadd and I will be able to do debugging of my libadd, so step my library. So A is equal to 1 and B is equal to 3, and then return, and then we will see here that 1 plus 3 equals 4. Okay, so again, when I'm done, I need to remove the symbols, so I will do it manually this time. And you need to remove the symbols for add, and add has already been executed, so it's killed. Okay, so the next example, or the last example, will be how to handle threads. So threads are running inside of one application, so one application can have multiple threads, and the thread is sharing the same memory, so it will be in the same virtual address range, so the same space ID. So I will open demo handling threads, and I will start the application called threads. So there we go. So I've stopped here at pthread create. So when I step this, you will see that threads will be created. So now you see I have 4 new threads. They have individual process IDs, but they have the same space ID. I have put a breakpoint in a function below called memWriter. So the memWriter is a function that all of the threads are using. So when I hit the breakpoint, you will see here that it was thread with process ID 552 that stopped. You also see up here which one it is. So let's go ahead and make the breakpoint a little bit more advanced. So we can change this. So we go to the Advanced tab and we go to Task, and we say that if it's thread with process ID 555, this is the only one that is allowed to break. So now I put in a condition, and if I run, it will take somewhat longer to hit the breakpoint, and now we see that the breakpoint that was hit is thread 555. Okay. Also, we can put, so to put a breakpoint, all you need to do is double click somewhere in the data list window. But we can go ahead and make the breakpoint a little bit more interesting. So let's say I want to put a read or write breakpoint at mem9. So I say advanced, write with condition. So I will put it as an on-chip breakpoint. And I will say that if someone is writing to mem at position number 9, I will break, because this is happening at 3 places, in the for loops and in this line 102 as well. So when I run, you will see that thread is being hit, and you see that it's stopped by a read-write breakpoint. So we can also go ahead and specify a data value. So counter is now equal to 14. So if we go ahead and say word, and we say 16, the dot after 16 is to denote that I'm meaning decimal number and not hexadecimal number. So let's put in this breakpoint. So if someone is writing 16 to number 9, we will break. So there we hit the breakpoint, and if we have a look, we see that we can open this, and we can see it in the watch variable. So this is not yet written, but if we have a look at the register value, we see that we will write the value of R2, which is 10 hex, which is 16 des, to, sorry, let me just put the spotlight here so you see it more clearly. So when we step this instruction, the value 16 will be written to 9. So this is type of conditional breakpoint which you can use. Also, you can use, so if we put the breakpoint in again and we say change, let's put it as an on chip. So we can also put conditional breakpoint. So we can say if counter is equal to 18, we would like to break. So this is something like if you have a threshold that you need to check before you do something. So if I run this breakpoint, or if I run the code, I will stop at this breakpoint because counter is equal to 18. So if you have some threshold that you need to check before you do something, this is one way to do it. And lastly, with the breakpoints, I'd like to say that you can also access the command line with the breakpoint. So this is typical if you have like a piece of code where you take care of errors. If you come to this piece of code, you can execute a script, a Lauterbach script, which will do some saving of some variables, perhaps looking at some RAM or memory, or checking some status of something else. So with this CMD, you will be able to get access to the command line. However, I will just say print and say breakpoint hit, and then I do not wish to resume execution. Okay, and so you see here breakpoint hit, which was written in the area window. So every time I'm hitting this breakpoint, this Lauterbach command will be executed. Okay, so this is the last thing I will show today. So it's called the performance counters, the benchmark counters. So this is counters that are using the on-chip resources for Cortex-A. So I will measure certain events. So this is the events I can choose from. So I've picked data cache dependent stalls, translation look-aside buffer miss dependent stalls, and so on. So we can also get them as a ratio. So we say x divided by clock, and we see how much of the total CPU time we have these misses. I can of course get them in a profile chart as well. So if we say this one, we say full, we can zoom in a little bit like this. So we can see how much of each event we have in each time. However, because we don't have trace yet, I can't correlate this to a piece of code where this was happening. So to know at what time or at what code was executing, you need trace hardware as well. I will show you this tomorrow though. So this is this is it for me. I will, so thank you for listening. So tomorrow I will do trace, what you can do with trace, and then Thursday is API and how to use Lauterbach in continuous integration. So I will unmute you all so you can post your questions.